Well, thank you, Paul. That's a very good introduction. I might just go on to the technical stuff now. But I do want to talk about Ethereum and like the second system effect and like where things have gone not quite wrong, but gone stale in blockchain. But first, it's going to get technical a little bit at the end, and if you don't like that, it's fine, get a beer. But my aim is that by the time we finish, you understand what we're doing, why it's important, and how we're doing it. So feel free, ask questions. Anything that is not clear, I'll try and answer them. So let's start off with what we're doing. So we're a new blockchain. And by that I mean we're completely new. All the code is new. We're based on F# and Fstar, which I'll get to. There is basically no common code with Ethereum at all, or Bitcoin, except for the cryptography. And I want to talk first about why we did it this way. So this is what we're doing. We're doing financial-focused blockchain, meaning that we're focused on creating instruments and doing things that are financial, collateralization, derivative-based mechanisms, assets. All those things are supported at the protocol level. And by focusing on that, we end up with something that is good at it. Not just a world computer, something that is good for financial use cases, which we believe is what a blockchain is best suited for. And if we're going to talk about blockchains, we should talk about Bitcoin. Bitcoin had the idea of a new kind of money, money that you just owned, that it wasn't conditional on someone else. It wasn't like a dollar or a pound note. It was more like gold, except unlike gold, it was digital. And unlike gold, it didn't depend on physical possession, it depended on a new thing, proof of work, a kind of global consensus in which a game theory guarantees in some way that there's an agreement on who owns Bitcoin. And when you compare it to other assets that aren't money, you find a big divide. You find that conventional instruments are very like fiat money. They are issued by someone. Normally they're regulated in some exchange. And whether you own them or not depends on a whole variety of social conditions. That also goes for creating them, of course. You can't just go out and issue a derivative. You issue a derivative either over the counter and you're still regulated, or on an exchange, in which case you never really see the derivative. All the collateralization, all the support for value is backed by a brokerage or by the exchange itself. And it leaves a kind of a gap, a lacuna. What if you could have outright ownership of digital assets? And Ethereum kind of tried to do that. You have these things called dApps and digital applications that could implement a kind of asset that people are trying right now to implement digital assets in. But is that really what Ethereum is doing? Ethereum is really doing a kind of world computer where everything exists in the same space, and you can do literally anything that you might be able to do on like Commodore 64. Okay, you can do it in Ethereum. Except that doesn't work properly, because if you make a mistake in Ethereum, then your investors or the people who own your assets, they discover that they didn't really own what they thought they owned. They discover that the backing isn't there anymore because there's a flaw in the smart contract. And the only exception is if you are so large that the fate of the blockchain itself depends on what you're doing, well, then there's a social consensus to kind of bail you out. And that's actually happened. And then the question always remains afterwards, is it going to happen again? Is Ethereum really an immutable world computer, or is it something else? Is it just a social consensus that is mediated via some code that doesn't really matter? And we thought we could do something else. We thought that if you target financial assets And if you do what is necessary for financial assets to be secure, to be capable of real financial properties like collateralization, with proof that that's what's going on, then you can have a truly worldwide or truly global system of financial assets. And we thought, okay, Bitcoin's already doing that, but just for money. So let's link it to Bitcoin. And we have links to Bitcoin, and then you can get Bitcoin value onto the Zen protocol. And then you can, for instance, purchase assets using Bitcoin without the need of an intermediary. Okay, and now it's going to get technical. Why did Ethereum have these problems? There's a couple of reasons. Firstly, because it's literally just a computer. It's an emulation of a computer that doesn't have any security properties itself inherently. The other problem is it takes a long time to do things. If you've seen various situations on Ethereum where you're trying to transfer an asset that isn't just Ether, like a token, the tokens aren't really recognized in Ethereum, not at the protocol level. Tokens are an application, just like any other sort of application on a computer. And that's slow, because they're interpreted applications. And we do not think that interpreting is scalable. We do not think that a computer that is literally interpreted one line at a time is going to be as efficient as it could be. So we thought of something else. We thought, what if you can determine how long these things take to run, how long a contract, a piece of code takes to run? Well, if you can do that, you don't have to interpret because you don't have to watch it anymore, you have to monitor it. And if you can do that, then you can compile the contracts. In other words, they can be just as fast as anything else that runs in your computer. And that is one of our technical advances. Beyond the support for native assets, beyond all that stuff, we have no VM, no virtual machine. And that really is faster. It's at least 10 times faster, and it gets even more fast as you scale up, because in an interpreted paradigm, you have to do one thing at a time. You cannot parallelize. You don't have machines, you don't have hardware support for parallelization in an interpreted setup. Whereas if you have multiple compiled contracts, even before you make optimizations, like software optimizations, okay, there's already a lot of research into how to make software run faster. And your processor is already going to make use various tricks to make your contracts run more quickly. And that gets us more capacity. There's a feeling that you can make things go faster on a blockchain. You can't really make them go faster. Like, it always takes a certain amount of time for the entire world to come to consensus on transaction history. What you can do is you can have more capacity. You can handle more transactions. And we try to max that out. We don't think everything is going to be okay on chain, but like we think quite a lot. You can get much better than you're doing right now. Okay, you can't really see it here, but this is kind of the fundamental difference between what we're doing and what other people are doing. We have agreement on code. So you see there Fstar code. That is our name for our programming language. And we have consensus on that. In other words, when you put contracts onto our network, you're putting code onto our network. Like little pieces of programs in a format that people can read and understand. That is not the case for Ethereum or for other blockchains. They put on something called EVM bytecode, which is opaque, you can't understand it, and that's the stuff that gets interpreted. Okay. Then what we do is we prove how long it takes to run. And once we've proven it, you can just compile it. And then each individual node, each individual computer can validate the Zen protocol network at machine speed. By contrast, if you're looking at Ethereum, you're looking at a consensus on the interpretation of this bytecode. One thing at a time, one action at a time, one account at a time, in fact. It just makes it a lot slower. That's basically how it works. It's still quite technical to create things. The developer support is coming along. What I'm trying to do here is to get people interested, developers, early adopters, in what you can do with this protocol. It is not the same as Ethereum. It is not the same as existing blockchains. It works in a different way. We think it's a smarter way. these contracts run much, much faster than Ethereum contracts. They run much faster than any other contract that works on the public blockchain. And the reason they do is because they can actually run as compiled code. It's a simple thing, but it's something that other chains just can't do. And we think it is going to make us not just more capacity, but more security. Because the language we're using is not just for proving how long contracts take to run. It can also prove what they do. And if you can prove that your asset is backed on-chain, and then your assets can talk to each other, and they become much more complicated, and you as a human being or as a trader, you don't have to understand that complexity. And I think that is it. Thank you very much. We think we can do, in an optimized version, about 60 transactions per second. That is taking into account that some transactions don't have a lot of signature verification and like complicated crypto stuff. Like it's more than Ethereum, it's more than Bitcoin. It's not that much more. It will scale up a lot more. What I mean by that is, with the various optimizations that we're putting in right now, we will easily see like another factor of 5. And then we support off-chain transactions. Off-chain, like layer 2, if you're familiar with that, like Lightning. We're pretty good at supporting that. But that's for the future, but right now we're looking at 60. There's a couple of ways. If you're prepared to be public about your identity, then I can just issue you a certificate of identity, and then you can use it. And there can be a contract that only accepts your requests if you produce your identity. If you want it to be private, it's more difficult. You have to use more advanced Lightning techniques. So we're in discussion with some groups, like zero knowledge proof researchers, in how you can have a privately issued identity that you can still have a contract that depends on what it's doing, but you don't reveal your identity. So what that means is that you're using a public blockchain, and you're using a contract that will only do what you tell it to if, for instance, you've received a certificate from a regulator, let's say, but you're not revealing who you are, not to the whole public. Okay, we're all based in Tel Aviv. We've got some English people, Americans, and Israelis. We've got some people like from like the .NET related community. So, for instance, our VP Research and Development is a senior engineer in C#, and he's transitioned to F# for this project. And Asher Manning, who's here today, is a recent graduate working in formal methods. So when I talked about proving what contracts can do, a lot of that is based on these formally verifiable ways. So we're not just F#, we're also Fstar. They kind of link together. So we're talking about functional languages here. Languages where things, you don't have variables that get updated. In other words, if I say like let x equals 5, next is always going to be 5. It's like a mathematical equation. It's not like I'm writing the number 5 into some like address somewhere. Why do we have that? It makes the proofs easier. It makes the proofs of how long something takes to run faster, more efficient, and easier to write. In fact, we don't write proofs that they're deduced automatically by our system, which is very convenient because like most people don't want to use computer science techniques when they're writing a smart contract. And F# is just you get the integration with like the Fstar advanced type system, advanced programming language. So you pay for computation the same way you would pay for any other transaction in the network. If you assume already that you know how long something's going to take, then you can just give it a weight. And you say, okay, we have a limit per block of 1 million computational units. And then you compete for it the same way in Bitcoin. You compete for space in the blockchain. Except instead of competing for space, you're competing for computation. to some extent, competition is unavoidable, and it's going to drive eventually traffic to like layer 2, like I say. We've got more headroom, so we've got much more time until that becomes an issue for us, like I said, a small beginning blockchain. But ultimately, if it's a public blockchain and everyone in the entire world is going to agree on everything, then there's a fundamental physical limits on how fast that can happen, and how much stuff you can agree on. And the solutions that Ethereum has proposed, like sharding, for instance, rely on not doing that, on not validating the entire blockchain. And we're also going to rely on that, but we're looking at the best ways of doing that, whether it's sharding or whether it's like other forms like Lightning Network. Just to deal with what you're saying about the halting problem. You're right, the halting problem is a theorem that says you can't prove how long a computer program takes to run, in general. Like there's no computer program that you can give other computer programs and it will say, okay, this takes X amount of time to run. You can't do it. It's true, obviously, but we don't prove all programs. If you can't prove how long your contract takes to run, you can't activate it. You can't put it onto our network. And most contracts that people run in the real world, they know how long they take. Like you don't want to put a program out there that could theoretically take forever to run. You want to put out a program out there that you know is going to give you a result, and it's going to give you a result in a reasonable amount of time. And that's what we let you prove. You prove how long specific programs take to run. And that's how we get around the halting problem, by not dealing with all programs, just the ones that we care about. CLR is not really, it's a very virtual machine, because you don't actually run stuff in the virtual machine. It does something else called just-in-time compilation. In other words, you have a model where it's a virtual machine, but what actually happens is the code gets compiled. So we take our Fstar code, we work out how long it takes to run, we turn it into F# code, we compile it to CLR code. It's a bit complicated. Then the CLR eventually is going to compile it to machine code. And what the actual effect is, it runs at machine speed. Whether you have this like idea of there's a VM or not, it doesn't matter, because what actually happens is it runs at machine speed. Okay, that's my colleague Ash. We're going to talk about oracles. Our oracle model is based on information from outside of the blockchain, from trusted sources, trusted by the people who are using them, not just trusted in general, which are very efficient and that give the oracle operators compensation. So we are looking at the paradigm of you're going to put information in a kind of hashed or concealed form, and then for every piece of information that someone wants to use, they will pay you for that information. So this is just using like very well-known at this point techniques like Merkle trees and proofs of inclusion. But it's like it seems to us to be the simplest way of having trust information with payment for that information, avoiding the problem of oracle information being just rebroadcast and becoming devalued on that basis. What we said, second quarter of 2018 for our mainnet, and that's what we've done. At the edge, on the 30th of June, we released our mainnet, and we have a running blockchain, as you saw, with smart contracts that can issue assets and do all that stuff, and has the proofs of cost and all that stuff. Staying on our roadmap, what we're looking at next is like clients, improvements to our contract language, improvements to our SDKs. We're staffing up right now. We're looking for developers. We're, not just to develop on our blockchain, also to work with us directly. We are getting out there and building connections with the financial community, with governmental organizations, and with small businesses. We think there's something there for all three of those groups that I mentioned. They don't all have the same requirements, but the general idea of financial applications is something that we're putting a lot of work into to make sure that these groups can actually use them for financial applications. So yeah, it's focus on what we're trying to do, which is financial assets with real financial properties on a public blockchain. I'm not sure. There's some stuff we're looking at. Logistics is, we don't think logistics is being done right now. Is people do want to use a blockchain. It cuts through a lot of the technical debt and the inertia in tracking stuff moving around. And that's something that we can do very well because we realize these objects as digital objects on our blockchain recognized at the protocol level. So maybe we could look at going in that direction. Maybe we can see support for that. Oh no, there's no need for that because like the whole point of the question is, would that be an independent blockchain? No, you can certainly take what we're doing and you can make a private blockchain if you really want to, but why do it? Like the whole point of this stuff is to integrate these things so that you have automated links and automated recognition of one autonomous system by another autonomous system, saving human beings the effort of computing this stuff, giving them better guarantees, in other words, the guarantee of decentralized automation. And plugging logistics into finance is one thing where that would apply.